Welcome to Chemistry with Caroline. In this video, we're going to look at the competition between substitution and elimination reactions for a secondary alkyl halide. So a secondary system is what we would consider moderately hindered. It has two R groups, two alkyl groups coming off of the carbon with the leaving group on it. The other factor influencing these reactions is the type of nucleophile that is added. So a nucleophile can also behave as a base. One molecule can have the characteristics to do both types of reactions. And so if we can characterize that nucleophile as either a weak base or a strong base, we can have a good idea of which way the reaction is going to go. As a system gets more hindered, weak bases are going to tend to go via substitution reactions. So they're not particularly strong bases, and for an elimination reaction, you do need to remove a proton. And so with a weak base in a secondary system, we'd be very likely to see a substitution reaction. Because of that sort of moderate hindrance and the moderate stability of a secondary carbocation, we can see a mixture of both SN2 and SN1 mechanisms for a secondary substrate. Which reaction path proceeds is going to depend on a lot of things, like the type of leaving group, the type of nucleophile, the polarity of the solvent. But there are some ways that we can figure out which reaction pathway proceeded by analyzing the products. And when we look at a specific example, I'll show you that. If you have a strong base, the more hindered the system, the more likely a strong base is to give an elimination product, because it can come to the periphery of the molecule as opposed to going all the way into the carbon atom. And so with a strong base in a secondary system, you'll see elimination. Strong bases are very good at plucking off protons, so you see E2 concerted elimination. In this example, I'm starting with a secondary carbon that has the leaving group on it. So our secondary kind of moderately hindered system, and then I have a nucleophile. This starting material is chiral. I'm starting with one stereoisomer here, and an SN2 reaction is concerted and happens all in one step. So you see only one stereoisomer produced from that inversion of the backside attack. So you have a nucleophile that comes in as your leaving group leaves. And because that happens, you only are going to see what we'd call the inversion product. So this H is now going to be poking out, and the nucleophile is going to be in the back. It came in the back side as the leaving group left out the front side. So we only see the inversion product. So if you start with a chiral starting material and you get a stereo-specific reaction, then you know that that's an SN2 mechanism that was proceeded through, because the only way I can get just one stereoisomer is if it's a concerted attack. So this is what we call a stereo-specific reaction, because you start with one stereoisomer and you get only one stereoisomer on the other side. In this example, I'm starting with the same starting material, but I see a different distribution of products. So that suggests a different mechanism for this reaction. And so you can see that I have both what would be called the retention product, which is on the left there, and also the inversion product. So the retention product has the nucleophile on the same face that the leaving group had been on in the starting material, and the inversion product has the nucleophile on the opposite face. So to have a 50-50 mixture like this is called a racemic mixture. And it means that I have equal amounts of both stereoisomers. So those are stereoisomers of one another. They have the same connectivity, but a different spatial relationship. The other way that I could draw that to show that there's no stereochemistry is to just draw a line there where the bond is, instead of using wedges and dashes, because then I'm indicating that it's not a chiral mixture. You have equal amounts of each stereoisomer there. So for this to happen, this has to proceed through an SN1 reaction. Our leaving group must leave and give a carbocation intermediate. And that carbocation intermediate is planar. It's sp2 hybridized at that electrophilic carbon center. So there's three things coming off of there: the isopropyl group, the methyl group, and a hydrogen that I don't have drawn because of line angle formula. And the nucleophile can come in either the front or the back. And because it can come in the front or the back, you're going to have equal attack on both sides, and that's going to give you your product mixture that you observe there. So we use equilibrium arrows with an SN1 type reaction because the steps are reversible. The leaving group can leave, but it would also be attracted to that carbocation, so sometimes it can attack it again. The nucleophile can come in, and then the nucleophile could also pop back off again. So I've used these equilibrium arrows here for that type of reaction. So this is an SN1 reaction, and I know that that's so because I see the racemic mixture as my product. So if you start with a chiral starting material and you end with a racemic mixture, then your reaction pathway must have been an SN1 type reaction. The other type of product distribution that would suggest an SN1 type reaction is if you saw a rearrangement product, as indicated here. So we have our leaving group on a secondary carbon here, and then we see this substitution product where our nucleophile is on that same secondary carbon, but then we have this other product where our nucleophile is on a tertiary carbon, and it's on a different carbon than where our leaving group started. That can only happen if the reaction proceeds through a carbocation intermediate, and that indicates an SN1 type reaction. So if we look at this reaction here, my leaving group would leave, and that would give me this carbocation. This is secondary, and next door I have a tertiary carbon that is more substituted, and the more substituted a carbocation is, the more stable it is. And so you can see rearrangement where this hydride, taking the electrons with it, is going to shift over to that carbon. Now, this is not a reversible arrow because it takes energy for this to happen, and it's not going to shift back to the less stable carbocation. The activation energy for the reverse shift is way too high. So now I have a tertiary carbocation there, and this H is this H here. I've just drawn it on to show where it moved. You don't have to draw it on if you're doing the mechanism there. And then, with this new carbocation, you're going to have attack of the carbocation carbon, and that gives you that tertiary substitution. There's some long arrows here up here, and gives you that rearrangement product. So a rearrangement cannot occur in an SN2 reaction. It's concerted. It happens all at one time, and it avoids a carbocation. So both the presence of a racemic mixture, if you had a chiral starting material, and the presence of a rearrangement product are indicative of an SN1 mechanism. In this last example, we look at a secondary alkyl halide in the presence of a strong base. So a strong base is going to give us an elimination reaction, and specifically an E2 reaction. Remember, when we look to predict the elimination products possible, we label the carbon with the leaving group on it alpha, and the next door neighbor is beta, and beta prime, beta double prime as appropriate. So the left-hand side would be a beta carbon, and then the right-hand side is different than the left-hand side, so we could label this beta prime. It doesn't matter which you label which, but that helps you predict products. And then you would look to see how many possible stereoisomers you might have. So the beta product would look like this. And then if I look at my beta prime stereoisomer, I see that each side of the double bond has two unique groups on it. So each side has a carbon, and then there'd be a hydrogen that's coming off of here that we don't have drawn on. And so because each side has two unique groups, you're going to have stereoisomers possible. So your beta prime is going to have an E stereoisomer, and the substrate can freely rotate before the double bond is in place. So the conformation of the starting material will determine the stereochemistry of the alkene. Once you form an alkene, that bond is going to be locked in position at room temperature because of the pi bond. It can't freely rotate. So if the molecule is in a eclipsed conformation when the elimination occurs, then it will have both of those high priority groups on the same side, and that will be a Z stereoisomer. So if you don't know how to assign stereochemistry on alkenes, I have a video on that, so you can look that up after this. This is an elimination reaction, an E2 concerted reaction, and so the strong base is going to plug off the proton that's anti to the leaving group, so as to minimize electronic repulsion and steric repulsion. The bond between the carbon and hydrogen is going to break and form a new double bond, so my arrow ends in the middle of that bond to indicate that, and my bromine leaves all at the same time, And so then as byproducts, you would also have the conjugate acid of the base and, of course, the bromide leaving group. So that has been a look at competition between substitution and elimination reactions for secondary systems. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.